Hello everyone, welcome back to Basic Electrical and Electronics Engineering. Today we are going to discuss what is the relation between line voltage, phase voltage, line current, phase current in case of delta connection. Previously we have discussed this relation in case of star connection. So let's get started with delta connection. Here a three-phase delta connected balanced load is taken where the impedance of each phase is Z ohm. Okay, now let's identify where line voltages and phase voltages are marked. Here these are the supply lines, R, Y, B are the supply lines. So this IR, IB and IY will be line currents, IL. Okay, as it is a three-phase balanced load, so all the three line currents are same. This VRY, VBR and VYB are the potential difference across any two supply lines. So these are the line voltages. Now this Z impedance is the impedance of a single phase. This is one winding impedance, this is second winding impedance and this is third winding impedance which is connected in delta. So the voltage across this each winding is nothing but phase voltage. So this is phase voltage, this is again phase voltage and this VBR is phase voltage. And the current flowing through the each branch or each phase or each winding is called as phase current. So this IRY is phase current, this IYB also phase current and this IBR is also phase current. Okay. Now observe here, we want the relation between IL and IPH and VL and VPH. Here this VRY is the potential difference between this R line and Y line. This R point is here, also here, okay, also here and this is also R point. This Y point is from here to here, okay, this is RY. So potential difference between these two lines is VRY is line voltage and also the potential between this R and Y point is VRY which is phase voltage. That means by observation we can say that VRY line equals to VRY phase. That means in case of delta connected load, line voltage is nothing but phase voltage. This one relation we got here. By observation we can say that VL is equal to VPH in case of delta connected load. Now see for currents. We want now the relation between IL and IPH. Here see here, this is the supply line and this is the line current IR. This line current here also line current, here also line current up to this point. And at this point it gets distributed within these two branches. That means IR is the resultant of IRY plus IBR. Okay, but when it comes to this point, this IRY is outgoing but this IBR is incoming. That means we have to write here minus IBR. So IR is not equal to this phase current. This IRY is the one phase current, this IBR is second phase current and the resultant of these two is our line current. So we cannot say that IL is equal to IPH as we say in case of star connected load. So in delta connected load, IR is not equal to IRY, or we can say IL is not equal to IPH. Okay. Now let's see here. From diagram we have concluded that line voltage is equal to phase voltage. So we will get this equation VL is equal to VPH. Okay. And line current is root 3 times of phase current. Line current is IL and this is root 3 times of IPH. This is in case of delta connected load, because here IR is the resultant of these two, the summation of these two. Okay, these two. So IR is greater than this IRY, as we have discussed this while discussing the star connection. When we plot or draw the phasor diagram for the currents, line current and phase current, by using the law of parallelogram, we will get this resultant line current as a √3 times of phase current. And in case of star connection from phasor diagram, this equation we will get from phasor diagram. Okay, no need to draw it again. Okay, as we have already discussed in the star connection. So IL will be what? √3 times of IPH in delta connection. In star connection, it is IL is equal to IPH. Okay, and for line voltage and phase voltage, in case of star connection, VL is equal to √3 times of VPH. This is for star, this is also for star, this is for delta, and this is for delta. But three-phase power in star connection and delta connection remains same. So three-phase power will be 3 times of VPH into IPH into cos of phi, or √3 times of VL IL cos of phi in terms of watt. This is the three-phase active power we have in the three-phase system. Okay, let's solve a numerical for this. Here VL is 400 volt and IL is given as 10 ampere. Here we have to find the IPH and VPH value for delta connection. We know that for delta connection, we have got these two equations. VL equals to VPH and IL equals to √3 times of, IPH, √3 times of IPH. We have discussed these two equations. Now we are using these two equations to find this IPH and VPH. So first, directly we can say VPH equals to VL, and VL is given as 400. So required value of VPH will be 400 volt. The second is IPH. IPH equals to, in case of delta connection, we have this IL divided by √3 from this equation. So IL is 10 ampere divided by √3 is equal to 5.7 ampere. Okay, and this is our phase current in case of delta connection. In this way we can find easily with the help of these two equations. Okay, then where these three-phase circuits are used? In case of this is applicable in case of three-phase induction motor, three-phase synchronous motor, submersible water pumps, and various machine tool applications such as lathe machine, grinder, milling machine, and large factories and educational institutes where load is more, where three-phase supply is required. So it can feed the three-phase loads, whether it may be star connected or delta connected. Okay, this is all about the three-phase system. In the next session, we will discuss the transformer, new electrical device transformer, and its working principle. Okay, so till then, stay tuned and keep learning. Thank you.